Right, this is going to be the first lesson on Newton's laws. Right, now for the most part, this is just a review. Last year we went in depth through Newton's 3 laws. And the good news is, in this case here, there were no half-truths told to you, no oversimplifications. Everything that you did at that point is exactly the same as what you would be doing now. So the good news is, well, we've already done most of this. So because of that, I'm going to spend just a very brief amount of time talking about concept, a little bit more time talking about computation. Okay, now, Newton's 3 laws. First one was the law of inertia. Basically, an object in motion is going to stay in motion, an object at rest is going to stay at rest until an outside force acts upon it. That is the same exact way as Newton intended it. The only thing that's different between what Newton intended and what I described to you last year, well, it doesn't even have to do with the first law. It has to do with the second law. In the second law, forces cause masses to change their velocity over time. This is the only variation from what we talked about before. Forces cause masses to change their velocity over time. In other words, forces cause masses to accelerate. A little bit more specifically, the sum of the forces. Net forces will cause masses to accelerate. Because if you were to have just a table sitting here, and a box on top of that table, we're not saying that there are no forces acting on that box and that's why it's not accelerating. What we're saying is the forces that are acting on that box are stable. They're in equilibrium. There's no excessive force going one way versus the other. So by saying that, we're saying that the sum of the forces equal mass times acceleration. Now, the key thing to remember off of this is equilibrium status. Now, there are 2 different ways to have equilibrium. The first one is to have an object that is not moving. If an object is not moving, obviously its velocity is not changing. If its velocity is not changing, that means it is not accelerating. Right? So, the other way that you can have equilibrium is to have a constant velocity. So by having a constant velocity, I'll add a vector hat to that as well. By having a constant velocity, that will tell you that the overall acceleration would once again have to be 0. Because velocity, once again, means the speed in a given direction. If neither the speed nor the direction is changing, that means that it is in equilibrium. If you get in a situation such as that, what that is telling you is the sum of the forces are still going to equal the masses times the accelerations, but in this case the sum of the forces are going to equal out to be 0. Okay, now once again, we spent a lot of time working on this. One thing that we are going to spend a significant amount of time on now is free body diagrams. We spent a lot of time on it last year. This year it's going to be more important to keep things straight, because the big thing was last year everything was acting on pretty much straight axes lines. We had up, down, left, right. Now we're going to be spending a little bit more time with slopes, a little bit more time with inclines, things like that. And that means that in general, let me see if I can do this. If I can't, I won't. Yep, I can. All right. In general, our entire axes are going to be tilted. So, with that in mind, it's important to be able to draw these and draw them accurately. Okay? And then the third law. Right. Every action, there's an equal and opposite reaction. In other words, forces occur in pair. You cannot interact with anything else without that other object interacting back with you. Okay, you cannot push on a table without the table pushing back up on you. You cannot kick a ball without the ball kicking your foot. So, the fact of exerting a force on one object means that that other object has to exert a force back on you. Okay? So, this one here, concept-wise, we're not going to have to worry about. So basically, 1 and 3, I'm going to rely on what you guys should know from last year. If you're confused, refer to your notes from last year, read through the book, or see what happens from there. Right? If you still need my help, please ask questions. But 1 and 3, I'm just going to leave alone. You have already done a whole lot of this stuff already. We've worked the concept. What I want to work is computations. And with computations, that is going to be the second law. Right? On the second law, the key thing is to work with free body diagrams. Now, a reminder about free body diagrams. That means that all you're drawing on this diagram is literally the forces. You're not drawing any type of detail on the object. Okay, if I'm telling you to draw a pirate ship, okay, I don't want the flags and the sails and the Jolly Roger flag going off the top here. Yeah, it doesn't need all that detail. I don't need to draw the boards on this. I don't need to draw the ocean waves on the side. If I'm drawing a free body diagram of that boat, that's all I need. If I want to draw it as a base outline, I can draw a base outline so I know what I'm talking about. But it doesn't really matter. The big thing is understanding what forces are acting on it and how they're interacting. Right? So, let's start with a simple situation. Let's say we have a book sitting on a table. Alright, so here's my table, and there's my book. Alright, let's say that that book has a mass of 1 kilogram. Alright, so if I were to draw just a free body diagram of that book, I'm going to draw that book and nothing else. Now, the first thing that you should recall is all objects on Earth are going to experience a weight, which is just simply the mass times gravity. There's another force that interacts anytime that there is two surfaces touching. Anytime you have two surfaces touching, you're going to get a force that is called the normal force, acting perpendicular to the surface. Literally, the word normal force doesn't mean ordinary or everyday, anything like that. The term normal here is the mathematical definition of normal, which means perpendicular to a surface. So by saying that this is a normal force, we are saying that it is perpendicular in manner to the surface that these two are in contact with. This is going to be important, especially when we start talking about ramps, slopes, and any of the other crazy types of situations here. So it's important to remember that the normal is, first of all, perpendicular to a surface, and it is also due to contact. You cannot have a normal force acting when two objects are not touching. A normal force doesn't just naturally exist. It exists between two objects when they are touching. Okay? Now, in my observations of a book sitting on a table, I'm going to say that most likely that book is not accelerating. So what that is telling me then is the sum of the forces is going to be equal to 0. Now, it's important to remember, just like when we talked about projectile motion, the sum of the forces in the x direction must equal 0, and the sum of the forces in the y direction must equal 0. Just like before, these two must be separate, they must be segregated, they cannot cross up. Right now, the first thing, and the one that's very easy, since I do not have any forces acting in the x direction, well, that's easy. 0 equals 0. The hard part is here. So the sum of the forces in the y equals 0. equals. Now, once again, just like with projectile motion, it's important to dictate what direction is positive. I'm going to call up and to the right to be positive. So therefore, my normal force is going to be a positive force because it's pointing in the same direction as my positive, and my weight is going to be negative because it's acting in the negative direction. Alright, weight is mass times gravity. 1 times 9.8 is going to give me 9.8. So, 0 equals normal force minus 9.8. And for review, the units on those are going to be newtons. So that tells me that my normal force, when I solve this out with algebra, is going to be 9.8 newtons. Quick reminder here, if I would have found that this number were to be a negative, that means the direction that I had predicted it up here would be the opposite direction to what it in fact was. So in that case there, it's important to make sure that you're paying attention to what direction you're predicting and what direction that arrow indeed is. Now, if I had found out that the normal force was actually negative, it wouldn't be in this case, but if I had found that out, that would tell me that this arrow would be pointing the opposite direction instead. Okay? Now, stay tuned for the next video when we're going to take a little bit of a practice problem into a slanted surface instead of a flat surface. So, I'll wrap this up and move on to the next video.